everything I'm going to talk about today is going to be joint work with Ian Whitehead, well, all the new stuff. I'm going to first do some introduction, and it'll all be work in progress. Um, and I multiple Dirichlet series. Some of you, I'm going to begin with talking about multiple Dirichlet series, and multiple Dirichlet series will primarily be introduced primarily for their applications to moments of L functions. So that's how I'm going to motivate them. I'll talk about a problem in moments of L functions, and I'll say how multiple Dirichlet series naturally arise in studying it, and then after that, I'll generalize to a more general notion of multiple Dirichlet series. So the L function I'm going to talk about is a quadratic Dirichlet L function, and I've written it with a Legendre symbol. So the Legendre symbol here is like multiplicative in n and m, and when m is prime, it determines whether n is a square mod m or not a square. And I sum this symbol against n to the minus s to make a Dirichlet L function. And studying moments of L functions means I take a value of this L function. So I've taken here the critical value at the point 1/2. I raise this with some power, and I want to understand the average of that over my family of L functions. So I'm summing it over m in some range. I'm choosing m to be square free and congruent to 1 mod 4 just to make the L function nice, make its functional equation nice. And but you can also consider a more general moment. So rather than you don't just have to consider it at the point 1/2, you can consider it at a different point in the complex plane. And then once you're going to do that, because you have the kth power, you can interpret it as a product of k factors and take it at the product of values at k different points in the complex plane. Um, and so this is like a more general thing, but one thing that's apparent when you study moments of L functions is often, even if you're only interested in this moment at this critical point 1/2, to understand it, it's helpful to study the moments with the product of values at other points, because the structures appear there that are more apparent, that are kind of hidden when you're looking only at L1/2. So what we're going to consider this general problem, which of course is at least sufficient to study the original problem with a tuple of k factors s. And when L functions were originally defined, they were defined to study sums over numbers up to some x or primes up to some x. And it was realized that you could extend these to like infinite sums with n to the minus s, and you get like a complex analytic function, and you can integrate the function to recover your original sum. And if you have some understanding of the analysis of the function where its poles are, you can apply Tauberian theorems and things like that to recover analytic information about your original sums. And so that worked very well with L functions. L functions have been very useful for studying prime numbers. And so it's natural to try that thing again. We have this sum over m less than x, and we're going to convert it into a Dirichlet series by summing now over all positive m times m to the minus s. So we've added a k plus first variable s here. And if we can understand enough about the analysis of this complex function, um, in particular, if we can understand where it has meromorphic continuation to and where are the poles, then we hope to we should be able to use that to understand the original moment. So to that end, the first thing that we should observe is that this series with in k plus 1 variables has functional equations. Because the L function has a functional equation, and so you can take the functional equation and apply it to all the LSI terms, and you'll get a new expression which looks pretty much like your original expression after a change of variables. Um, And this turned out to be very useful for studying this complex analytic function because functional equations, just like in the classical case of L functions, they help you prove meromorphic continuation to a broader domain. They help you understand the rate of growth of the function on that broader domain. They basically help you with all the analytic questions that you have to try to eventually understand the sum. Um, so we definitely want to understand these functional equations and then hope to use that to uh, understand the meromorphic function, and then from the meromorphic function to understand the sum. And so to that end, we might observe that this series, it like feels like it should have, it almost has another functional equation. Um, and so the way to see this additional functional equation is to expand the sum. So each alpha function is the sum over n from 1 to infinity. We have a product of the k alpha functions, so that's the sum over k variables, n1 through nk from 1 to infinity. And the thing we're taking a sum of is going to be a product of these Legendre symbols. Um, and then we can reverse things. So Legendre symbols satisfy quadratic reciprocity. We can flip them over. We can use their multiplicativity also to kind of squish them together into one big Legendre symbol, and we get m over n1 times up to nk. And then we can also reverse the order of summation. We can make the n sum on the outside and the m sum on the inside. So any manipulation like that will be justified in some region where sum is absolutely convergent, and we can analytically continue beyond that. And so this series looks roughly like a sum now of alpha functions in this new variable s of the Legendre symbol to modulus n1 through nk, or the modulus the product of n1 through nk. It's not quite this L function because I put this additional conditions on the variable. We may have to make it square free, and we have to make it congruent to 1 mod 4. And so, but if it were an L function, it would have a functional equation, and you could sum the functional equation over n1 through nk to try to get a functional equation of the series. However, with these like missing terms, it doesn't quite work. Now you could say, it's just my fault that terms are missing. I said at the beginning to get rid of those values of m. We could have just not done that. But the problem is when you don't do that, it causes problems for the original k functional equations that you would have like because the conductor of the L function wouldn't just be m, uh, the sum applying the functional equations for each factors, they would all be different functional equations, and so they wouldn't give you a functional equation for the sum. So summing the functional equations only gives a functional equation for the sum when the individual functional equations all look similar enough. And so it seems like we're stuck. We can change the problem, we can modify things to make this additional functional equation appear, but we lose the functional equation we started with. But it turns out we're not stuck. And the reason we're not stuck, we can modify things in a more general way. And so we're going to consider a very general way of modifying this series to a series which is similar, but we've adjusted the coefficients, and we want to adjust it so that the functional equations appear. So we'll consider just a general Dirichlet series whose coefficients depend on parameters n1 through nk and m, and then we'll sum it against the m to the minus s and the ni to the minus si. And so we'll choose our coefficients so that in some nice range, like where m is square free and congruent to 1 mod 4, our coefficients agree with the original product of Legendre symbols. But outside this nice range, we're going to choose them to be something else. We're going to try to make it similar in terms of satisfying the same twisted multiplicativity conditions. I'll explain that a little bit later. We're going to make it similar, but we're going to give ourselves a lot of freedom to choose the coefficients. And it turns out when you do that, you can find a way to choose the coefficients so that both functional types of functional equations appear. So the original k functional equations in the SI variables, and then the last functional equation in S will all be valid equations for the series. Okay, and so now we're in good shape with extra functional equations. We can prove meromorphic continuation to a broader domain. And generally have good control on the function to do with growth conditions and stuff. And then this immediately won't help us with the original sum because we changed the series. But what you can do, because we added terms that are like non-square free, anytime you want to get rid of things that are non-square free, you do a sieve. And so we can do a sieve to subtract off the new terms we added and write the original series as like a linear combination of this new series and like a bunch of similar series. And analytic control on each one, you get analytic control in this linear combination, so you get analytic control in the original series. So you know where that has meromorphic continuation, you know what its poles are, you understand the growth, and that gives control in the original sum. Um, and the setting where this works very well is the kth moment for k at most 3. For k at most 3, we obtain meromorphic continuation to all of c to the k plus 1. And the applications to moments of L functions have been worked out. So I think this study was initiated by Goldfeld and Hofstein, and there was work of Diacono, Goldfeld, and Hofstein, and then some very strong calculations of cubic moments were done by Diacono and Whitehead. And you can do a little bit of information on the fourth moment in this way, but not nearly as much because you don't have as much meromorphic continuation. And so in particular, this leads to the best known estimates on the third moment of quadratic Dirichlet. And this is the first example of a multiple Dirichlet series. So what do I mean by a multiple Dirichlet series more generally? I don't think there's usually not a formal definition of this given in the literature. I'm going to give a kind of rough definition. So a multiple Dirichlet series should first be a Dirichlet series in several variables. So it's a sum of a n1 through nr times the same coefficient, product over I ni to the minus si. And we want for classical Dirichlet series, we usually take the coefficients to be multiplicative. In this case, we're going to choose them to be twisted multiplicative. So what twisted multiplicative means is if we have two tuples of coefficients, if we multiply them together element-wise, the coefficient of the product should be the coefficient of one tuple times the coefficient of the other tuple times a third factor, where the third factor is a product of Legendre symbols. So in this case, I've written a specific product of Legendre symbols, which is the one that's relevant for the moments of quadratic Dirichlet L functions. But you could have a different product of Legendre symbols than the one I've written down. You could have a product of other kinds of symbols, like higher order power residue symbols. And you obtain this when there's no common factors between the tuples. So when the product of the first tuple and the product of the second tuple has no common factors.
Hi, Will. Could I just, there's a question in the chat, if it might direct you to that. Do these L functions have interpretations in terms of a family of multi-quadratic extensions with k added square roots?
I think it is better to interpret it in terms of single quadratic extensions because we're yeah, like we're taking. So there's two ways to write this as a sum of product of L functions. We have the one at the beginning and the one at the end. And the one at the beginning, we have a product of L functions associated with the same quadratic extension, but at different points. So it doesn't make sense to think of that in terms of a multi-quadratic extension. And the one at the end, we only have a single L function. It's at a product of moduli, so you can interpret this as L function as one factor of the Dedekind zeta function of a multi-quadratic field, but you could also just interpret it more directly as the L function of a single quadratic extension. Yeah, I hope that's helpful. In general, I'm going to talk not so much about interpreting these series. Some people have studied heavily, like how do we like interpret these series, and in terms of like other number theoretic concepts. And I'm not going to try to do that in this talk. I'm going to just describe them directly by the properties that they have. And then the twisted multiplicativity on its own is not very interesting. So you have to put an additional condition. And so classically, what people require is these series should satisfy functional equations. And so like the you can phrase this in two different ways. So a minimum thing that I could request is for each of the variables si, there exists some functional equation that like flips that variable. It sends it to like one minus itself, or maybe 2 minus itself or something. It like flips that variable. Um, and the strongest thing I request is that I have enough functional equations that I could prove meromorphic continuation to the whole complex plane C to the R. And when I do that, I'm well set up to understand every property of the series basically, much like you are for a classical Dirichlet series when you have a single functional equation. So let me explain a little bit how that goes. How do functional equations let us prove meromorphic continuation to all of CR? And so you can start from the fact that the original, just looking at the series, it will converge on some domain in C to the R. And whether it converges depends only on the real parts of the SI variables. So the domain it converges can always be described as the inverse image under the map from C to the R to the R that takes a tuple to its real parts of a cone in R to the R. Um, and every time we have a functional equation, that gives us a new formula for the series. You can apply the functional equation and then plug in the sum. And this new formula will converge on some other cone. So it'll show that the series is holomorphic on the inverse image of a different cone in R to the R. So sometimes the functional equation, there's like a denominator in it, so you only get meromorphic and not holomorphic, but that's not relevant for the kind of convergence issues because you always take the denominator outside of the sum you're trying to show is convergent. But you don't just have access to the functional equations because each functional equation is relating usually the series to itself or sometimes to a similar series. So you can apply them in any order. You can apply the first functional equation and then the second functional equation and then the first functional equation again. And that gives you a new representation of the series, which converges in a new cone. So iterating the functional equation, there's lots and lots of different cones where the series converges. Um, and usually the cones don't quite fill up the whole space. But then you can apply Bachner's tube theorem, which says that any holomorphic function, or any complex function which is holomorphic on the inverse image of a domain in R to the R, automatically extends to a holomorphic function on the convex hull. So you only need to have enough cones that the convex hull of the cones fills R to the R to obtain meromorphic continuation on all of C to the R. And the picture that you should have is that the cones look like the Weil chamber decomposition of R to the R associated to some root system. If you know what that is the cones will be like the Weil chambers but shrunken slightly, but the convex hull will still fill space. And this can fail. Well, it can fail if you don't have enough functional equations. If you don't have a functional equation reversing a variable, there'll be like a cone, and you won't have another cone on a certain side of that cone. And so you can run into trouble that way. But the more interesting way it can fail is if you keep making cones and more cones, and you have infinitely many cones, but they still haven't filled up all of space. They can fill up maybe only a half space. Their convex hull is a half space, or the convex hull can just be a very big cone with a bunch of smaller cones inside it. But you always have infinitely many in this case because any finally many cones, you can always make a next cone after it with a functional equation. But if you have infinitely many cones, you can get stuck kind of converging asymptotically to something. Um, so a bunch of uh, these multiple Dirichlet series are known to exist. The biggest class of them that are understood are the Weil group multiple Dirichlet series, which have been studied by a bunch of different people. There's some important work of Brubaker, Bump, and Friedberg, and Chinta and Gunnels. And Weil group multiple Dirichlet series are parameterized by Dynkin diagrams, and all of the symmetries, the functional equations, will be controlled by the Weil group of that root system of that Dynkin diagram. So you'll have the cones will look exactly like the Weil chamber decomposition of that root system. Um, and they also depend on a choice of characters. So you can make them with quadratic characters, But if you work over a field with like d roots of unities, like a d cyclotomic field, you can make something with like a d order power residue symbol, and also with the choice of Dinkin diagram. However, it's only really the quadratic character case that's relevant to moments of L functions. The um, the others are relevant to other kinds of sums, which are kind of not as arithmetically motivated or not as immediately motivated. And these include the series that are used for the first, second, and third moments of quadratic Dirichlet L functions, which correspond to the Dinkin diagrams A2, A3, and D4. The general thing is to get the kth moment, you would want a diagram that's a k-pointed star, which is a Dinkin diagram for k equals 1, 2, and 3. For k equals 4, it's an affine Dinkin diagram. You have like an affine symmetry group, and the cones fill out a half space. And for k greater than 4, it's a hyperbolic Dinkin diagram, and the cones fill out like a smaller cone. And outside of the Wagner multiple series case, there's a few examples known. So if you're interested in the first moment of L functions of higher order characters, like you want to sum the L function of the character to modulus M for M in this D cyclotomic field over M with norm MO something, then there's a series which is relevant to that problem. If you somehow the coefficients, if you sieve it, you can extract this moment. If you're interested in the second moment, you have two choices of how to do that because the critical value of this series is not real. So you can take the second power with the absolute value, you can take the second power without the absolute value. So for the second power with the absolute value, the relevant Dirichlet series was written down by Diacono. And for the second power without the absolute value, it only works for cubic characters. So it doesn't work for higher order characters. And this was written down by Brubaker. And there's a couple other examples which are related to automorphic forms. So anytime you have the second moment of a Dirichlet L function from such a series, you can get also the first moment of the L function of a modular form on GL2, twisted by the Dirichlet L function. When you have the third moment of the quadratic character, you can get a modular form on GL3. And then for the first moment, you can do twists of automorphic forms on GL1. So the Weil group multiple Dirichlet series, there's like a beautiful theory. There's kind of a uniform construction of them. They're related in a nice way to automorphic forms, to Eisenstein series on metaplectic groups. They have some relationships to combinatorics and to other fields. And the other three examples are more isolated. Like you had like there's kind of not uh a general theory that unifies them. You have to be very clever to find these examples and come up with them. Um, and so that is what our work is trying to help with. So what we're doing is giving a construction of multiple Dirichlet series that is uniform, is not reliant on clever tricks to construct individual examples. Um, that includes everything I talked about in the previous slides. It doesn't include the automorphic. So our method probably could be applied to L functions with automorphic twists, but we haven't considered that case. And it also includes uh, dozens of new examples. Well, I mean, some of the examples are infinite families, so you could say we made infinitely many new examples. But if you count infinite families as only one, then yeah, then there's like 24 or something like that. And these are multiple Dirichlet series in the strong sense that I talked about before. They have meromorphic continuation to all of C to the R. Um, and much like the Weil group multiple Dirichlet series, most of them seem to have nothing to do with moments of L functions. However, some of them are relevant to moments of L functions. You can get some very weird moments that is not clear why you'd want to study. But you can there's two moments that you can get from this. that I think are interesting. So they're the L function, if you're summing over the Gaussian integer, so integers with the fourth roots of unity, the L function to a given modulus, a character of order 4, times a character of order, the L function of a character of order 2 to the same modulus. Or in the Einstein integer, so joining the six roots of unity, you can take an L function with a character of order 6 to the same modulus times a character L function of a character of order 2 to the same modulus. So these kinds of mixed moments of two different Dirichlet characters to the same modulus um, of have not yeah, I think should be interesting. I should be very clear. I'm not announcing any results about moments of L functions. So what I'm saying is that the Dirichlet series should be useful in the future to help with these moments of L functions results. Similar Dirichlet series have been similarly helpful to moments of L functions in the past, but none of the work of actually converting the Dirichlet series into a moment of L function result have we done. Do you have a question?
Yeah, hi, well, uh, so maybe you were answering it, but I wasn't clear. Can one not do these moments analytically by using an approximate functional equation or something like this?
Um,
These specific two examples, which are like glorified second moments of quadratic or fourth order characters.
so you could get hopefully by multiple Dirichlet series, you should be able to get like a better error term and like maybe see some interesting secondary terms, which would be hard to see using the approximate functional equation. Uh, but yeah, I don't know. Yes, I don't know what you can do by using the approximate functional equation for these kinds of weird second
Okay,
moment.
so that's probably a good problem to pose to the listeners. What can to I'm sure both methods will give the main term, but whether what you can do with the remainder term. And for instance, do you believe that there is a secondary pole here,
Um,
like a
so
secondary main term?
uh, so I would think probably just because the group of functional equations that appears is uh is complicated enough that it feels like there should be some poles producing some secondary main terms. I have not done any calculations to try to find the poles, see where they should be, like what the secondary main term should be. I think uh I think Ian may be working on that. I don't want to like, yeah, yeah, I don't want to talk. Yes, Ian may be working on that.
Okay.
Um, and so, but there's one big caveat that these results come with, which is that they're over FQT and not over the integers over a cyclotomic ring. So what I mean is that the formula I wrote for multi-Dirichlet series of sum over natural numbers is not what I'm really talking about. I'm really talking about a sum over monic polynomials of a coefficient depending on a tuple of monic polynomials times the analog of the ni to the minus si is q to the minus si times degree fi. So with q to the degree fi playing the role of ni. And so normally when I give a talk about summer's all function field, I mean, it's pretty common for people to ask, like, could the methods eventually apply to the number field case? And I always have to answer, like, no, like, there's no chance that these methods can apply. However, in this case, it's kind of the reverse. So there is some understanding of how to get multiple Dirichlet series between function fields and number fields because using the multiplicativity relations, the series are determined by their coefficients at prime powers, and you can take the prime power coefficients in a number field to be the same as the coefficients of a prime with the same residue field in a function field. And so, like again, we haven't done this, but it seems that like it should be possible to eventually transfer these to the number field and have the same construction in the number field setting as well. Um, and then now is a good place to pause if anyone has any other questions. Oh,
Yeah, while I'm on the roll, in an earlier slide, you were mentioning something about what happens if the cones don't, the convex hull doesn't fill up all Euclidean space. Now, in that case, do you know that there's no analytic continuation? That is, can you prove there's a natural boundary, or just that you don't know?
so in some cases, you can prove that there is no analytic continuation, and the method is you use in the functional equations, in the cones where you can prove meromorphic continuation, you can calculate the poles. If you show there are poles, if you have an infinite series of poles converging to
Okay, they
some
will pile up
hyperplane,
on
then you indeed
something.
have to have a natural boundary at that hyperplane. So this is a calculation people have done in some cases, uh, but it's certainly not true that in every case where we don't get verification to all of C to the R that has been checked.
Okay, thanks.
Um, okay, so let me continue. So let me say in a little bit more detail what I mean by uniform construction here, and then and how in broad terms does construction work. So I want to mention that first that multiple Dirichlet series are typically uniquely determined by their functional equations, and this helps in constructing them. But if there's a unique series that satisfies a given functional equation, um, and you can calculate what is the unique thing satisfying the given functional system of functional equations, and then that gives you a formula for the series. It helps you understand the analysis of the series as well. Um, and this is particularly good if you know in advance, before constructing your series, what functional equations it should satisfy. As, for example, happened in the Weyl group multiple Dirichlet series case, you use the Weyl group to write down the functional equations. You find the unique series satisfying these functional equations. But if you don't know what the functional equations it should satisfy, it leaves you in a kind of chicken and egg problem for constructing the series. You can't, if you want to construct the series using its functional equations, how can you find out what the functional equations are unless you already constructed the series? Um, so there's recently been developed a kind of axiomatic approach, which observes that over FQT, multiple Dirichlet series can be characterized by other properties that they have other than the functional equation. So one is the twisted multiplicativity property, and there's another key property which I'll call local to global property, which I'll talk about a little bit later. And if you describe that, you can write down a list of axioms which uniquely characterizes the series based on these properties. And then you always have a choice. There's different twisted multiplicativity relations you can write down, and for each choice of twisted multiplicativity relations, there's one unique series. So you just completely ignore the functional equations, and because you ignore the functional equations, you've kind of created some trouble. You don't know if the series you construct have functional equations. Some of them probably do not have functional equations in every variables. Some of them definitely do not have enough functional equations to prove meromorphic continuation to the whole complex, to the whole C to the R. So, by the definition I gave earlier, like maybe they're not even multiple Dirichlet series. They're just some kind of weird series. Although we like to call them multiple Dirichlet series. However, some of them do have functional equations, and you can figure out which ones have enough functional equations to prove meromorphic continuation. And this becomes a much more tractable problem. Instead of just trying to construct a series out of nothing that satisfies a bunch of functional equations and you don't know which ones they should be, we've defined this whole sea of series, most of which do not have the functional equations we want, but we have to just find the islands in this sea that satisfy the functional equations that we need. And so that's how the uniform construction works. There's this uniform construction, just parametric construction of this whole sea of series, and then we just identify within it the ones that meet our standards. Um, so let me say something about the nature of this C. So how do we parameterize our series? And so the key thing to observe is that FQT has the Q minus first roots of unity. And so you can use this to define a Q minus first power residue symbol or a version of a Legendre symbol of order Q minus 1. And then we just kind of write down it's sort of the most general twisted multiplicative relation you can think of. Every term, fi over gi, every can appear to a given x to any desired exponent mii, and the fi over gij term should appear to the exponent mij. The thing has to be symmetric, so the gi over fj term appears to the same exponent. So these choices of twisted multiplicative relations are parameterized by these R by R symmetric matrices that tell you what exponent to raise these different residue symbols to. And the series you get can vary a lot as you change this matrix M slightly. But if you have a specific arithmetic problem you care about, like a specific moment, it's not too hard to calculate which matrix M can get you a series that might help you with that. It just depends on finding what's the twisted multiplicativity relation that the terms in the series you originally care about satisfy. And so I'll know that for moments of L functions, you care about M which have this particular special form. They're like block symmetric matrices with the two blocks on the diagonal vanishing. One block is coming the variables that are the conductor of the L function, and the other block is the variables that are the parameters being summed over. In the L function, they don't interact with themselves, but they interact with each other. So let me say something about what this local to global relation is. And so one way to think about where this relation is coming from is that for these series over FQT, there's really two different things that you could refer to by the coefficients of the series. So the most obvious thing that I could mean by coefficients is just these functions a, f1 through fr, which are the coefficients. And because of its twisted multiplicative relation, to determine af1 through fr, I only need to know the coefficients at prime powers, when the tuple f1 through fr are all powers of the same prime. But the other thing I could say is this series is a power series in the variables q to the minus si. And a formal power series, and I could just look for the coefficient of a monomial in that formal power series. And then because the same term q to the minus si degree fi occurs for multiple fi of the same degree, the coefficient of this power series, which I'll call CE1 through ER, is a sum of many terms AF1 through FR. And so they're both interesting to understand when we're studying the series. And one thing people observed, I think this observation was first made systematically by Cinta, is that if you write down a formula for these coefficients, local coefficients at a prime power, a pi to the e1 up to pi to the r, you write down a formula for the global coefficients CE1 through ER, they look very similar. You can like write them as formulas with like the same number of terms. However, they look similar in a strange way, which is terms which are very large in one formula correspond to terms which are very small in the other formula. So there's not any kind of usual analytic relationship between them, that there's some equation that the A and C satisfy. It's a subtler thing, and you can describe it precisely in by expressing both of them as sums of V numbers, which it turns out you can do in a canonical way. You express them as sums of V numbers, and you can relate the V numbers appearing in one sum to the V numbers appearing in the other sum by a funny process. You have to divide by some power of q, take the complex conjugate, you have to invert it, and then raise it to the power of degree pi. And I think this inversion step is the most interesting because it does this weird thing of swapping small terms for big terms and big terms for small terms. Um, and then Diacono and Paschal, and then also so Whitehead had this idea to not just to take this observation of the series and use it to define or construct the series, to take this and the twisted multiplicativity and a couple other axioms and show that they uniquely determine the series by some inductive argument. You have like a bunch of relations between the coefficients, and you can inductively show that each coefficient is determined in turn by these relations. But they were only able to do this in the case of quadratic characters, and then only able to prove it exists in certain subsets of that. But a few years ago, I worked out how to make this construction, how to define it, write down the axioms, and to show that they actually exist unique things satisfying the axioms in general. And so after defining these things, the first step in our work is to establish as many functional equations as we can for them. And let me try to make a little bit more precise what I mean by just establish a functional equation. Um, and so the way to figure out what's going on is to kind of zoom in on this complicated series. You're going to fix all but one of the variables we're summing over and just restrict attention to the sum over a single variable fi. And what you can observe using the twisted multiplicative relation is that one variable sum looks like a one variable series that you may be more familiar with. It could look like a Dirichlet L function, or it could look like, sometimes it looks like Kubauda's series of Gauss sums. And so in the Dirichlet L function case, what I mean by look like is more precisely it like is the Dirichlet L series, except after changing finally many of the Euler factors. So all but finally many of the Euler factors agree with the Euler factors of the Dirichlet L function. And so that tells you what functional equation you should expect it to have. You should expect it to have a functional equation that looks like the functional equation of this Dirichlet L function. And so when we say we established a functional equation, what we mean is we checked the functional equation of this Dirichlet L function. It still holds as a functional equation for this modified series in one variable, and then when you sum it over all the other variables, you still get a functional equation for the multivariable series. Or in the Kubota case, Kubota showed a functional equation for his Gauss sum series, and then we check it still holds for the modified series, and then you sum it, and it holds for the multivariable series. And so this was done by Whitehead in his PhD thesis for the case where you get a Dirichlet L function, but specifically where it's a quadratic Dirichlet L function. And he did it by an inductive argument using the axiom to show you first get the functional equation where the degrees of the other fi's are small, and then for larger and larger and larger degrees. And then my student Hasliu did the general case of the Dirichlet L function by a very different argument, a geometric argument, using a kind of geometric understanding of these series. And we are establishing a Kubota type functional equation. So the functional equation when it looks like a Kubota series, again by an inductive argument similar to Ian's thesis. And we also check that this gives an alternative proof of the Dirichlet type functional equation. So we have two proofs in that case. And so now that we have the functional equations, we can set up this problem more precisely for which parameters, for which values of this matrix M, do these two types of functional equations that we found suffice to prove meromorphic continuation to all of C3R. Which becomes a question about like what cones we get in R to the R from these functional equations, and do the cones fill up all of space, or do we get stuck somewhere, or do they get asymptotic to a half space or a smaller region? And so it's some kind of purely combinatorial problem. So already we've like would have greatly improved the situation from having to construct some unknown object to now just having to solve some kind of combinatorial problem. But it's actually even better than that because the combinatorial problem has already been solved in the literature. So we found that it was solved by Istvan Hackenberger as when he was thinking about something that seems to be totally different, which is the classification of finite dimensional Nichols algebras as diagonal type. And I won't say what that is, but I'll say that his classification involved first classifying, or it was essentially equivalent to a classification of arithmetic root systems, which are some generalization of the classical notion of a root system. And what we see is that you get a Merrill-Dirichlet series, which our functional equations prove uh, is meromorphic almost everywhere. For every arithmetic root system constructed by Heckenberger, as long as it satisfies a certain technical hypothesis. Um, and so, with regard to Zaev's questions about when you can't prove meromorphic continuations, uh, is it because it's false or because you just don't have the proof yet? So when the technical hypothesis is not satisfied, we believe that there should exist a more general functional equation that does give meromorphic continuation. We just haven't proven that functional equation yet. Um, but even with the technical hypothesis, there are lots and lots of examples. So all you have to do is you have to go down this list that Heckenberg created and just cross off all the examples that don't satisfy the technical hypothesis, and you get this list of multiple Dirichlet series. So I've written this list for you right now. I don't expect you to like understand this list or find it particularly enlightening, but let me like just kind of explain some properties of it. So the ones whose names might be kind of familiar from studying Lie groups, the A, B, C, D, E, F, G at the beginning, are uh, are the ones that correspond to the Weyl group multiple Dirichlet series. So those are the ordinary Dynkin diagrams. Those have been well understood. Then the next set, which have like a lot of parameters, the A, B, C, D, D, F, G, are all root systems of super Lie algebras. So the Lie algebras in graded vector spaces. So there exist such things, and there's root systems, and they correspond to multiple Dirichlet series. And a couple of the examples that are previously known are type A here. So they're super versions of SL2 and SL3, or of SL3 and SL4. And And then the next examples are mostly about Lie algebras and characteristic P. So there's simple Lie algebras and characteristic P that don't lift to characteristic 0. And there's simple super Lie algebras and characteristic P that don't lift to characteristic 0. And those have a notion of root system. And to those root systems, it turns out they're also often correspond to multiple Dirichlet series. So the WK is in characteristic 2. A bunch of the G's are in characteristic 3. I think G26 is the one that corresponds to Brubaker. Uh, then the ones with a 5 at the end are in characteristic 5. That's BRJ25, and there's EL55. And the last 4 are UFOs, and it does stand for unidentified flying object. And they're called that because they have no known connection to any sort of generalized Lie algebra. The only algebra they have a known connection with to is this Nichols algebra of diagonal type. Um, and so there's 12 of those, and only 4 of them satisfy the technical condition, and those all correspond to multiple Dirichlet series as well. Um, okay, I think I'll stop there.